recording. All right, we want to find, well, let me give you a moment to copy this example down. Okay, all right. So linear approximations. Okay. All right. So in this problem here, we want to find the linear approximation of the function f of x equals square root of x plus 3 at a equals 1. Okay, and we'll worry about that in a moment. And we're going to use it to approximate the numbers, the square root of 3.98 and the square root of 4.05. And then are these approximations overestimates or underestimates? So let me ask you, all right, like the square root of 4, what's the square root of 4? 2, sure. Okay, what's the square root of 3.98? How would you find that square root? It's just about equal to 2, not exactly 2. Certainly in astronomy, if it were an application involving astronomy, that little difference could be important. I mean, how would you find the square root of 3.98? I mean, how would you do that? Well, I mean, how would just sort of how would you just, if somebody asked you, hey, what's the square root of 3.98? What would you do to? Well, okay, but suppose you didn't want to guess. I mean, okay, use a calculator. All right, use a calculator. Okay, but then the question is, how does the calculator get that answer? I mean, okay, the calculator is going to give you a pretty accurate answer for the square root of 3.98. But how did the calculator do it? Okay, what programming is involved in the calculator that can get that approximation? Okay, so this is why we want to understand about linear approximations. Okay, so let's go ahead here and first of all, what I'm going to do is I've drawn the function here. I've drawn the function f of x equals square root of x plus 3. Okay, I've drawn the function. Here it is in blue. Well, I mean, you see the picture there. Okay, and it's the square root of x plus 3. So, of course, if you take the square root function and shift it 3 units to the left, I mean, we all know what a square root function looks like. Take the square root function, shift it 3 units to the left, you're going to get the function that is shown here. Now, at 1, 2, what is that I've drawn at the point 1, 2? You know, 1, 2 is on the square root. If 1, 2 is on the function, because the square root of 1, you know, if x equals 1, square root of 1 plus 3 is equal to the square root of 4, which is 2. So the coordinate 1, 2 is on my function. What is this L of x line that I've drawn? It's a tangent line. So, hey, the tangent line to the function f of x equals square root of x plus 3 at the point 1, 2 is given by this y function, which I call L of x. And the reason we use L of x for y is because it's going to be what's called a linearization. The tangent line is a linearization of the function. This tangent line here is a linearization of the function. The function's nonlinear. The function's nonlinear. But if you restrict your attention, okay, around point 1, 2, if you restrict your attention, oops, hold on, I have to take the thing off. If you restrict your attention, maybe where that circle is, and that would correspond to this interval here, this interval of x, okay, maybe from like 1/2 to maybe 1.5, something like that, maybe like something like this, okay. If you restrict your attention to the interval maybe of like 1/2 to 1, you know, x equals 1/2 to 1.5, does this tangent line approximate our square root function pretty well? From say, you know, 0.5 to maybe, it's not perfect what I'm doing here, but let me fix it a little bit here. Okay, so from 0.5, from x equals 0.5 to x equals 1.5, okay, would you say that line approximates the function reasonably well? In other words, does our function square root of x plus 3 basically look linear between the values of, between like from x, between the values of x equals 0.5 to x equals 1.5, okay, does our tangent line, does our function seem to be approximately linear? Does the function basically, yeah, I mean, over, in that range, when x is between half and 1.5, which is, if you focus in the circle here, okay, that's when x is between a half and 1.5. The function square root of x plus 3 is it's reasonably well approximated by the line. And so that's what we mean when we say we want to find the linearization of the function. That just means I want to find the equation of that tangent line. And so you've done this many times. You have your function, which is x plus 3 to the half power. You want to find the tangent line to the function at the point 1, 2. So you're going to take the first derivative, evaluate the derivative when x equals 1, and then you're going to find the tangent line. Okay, so as you know, y minus y naught equals m times x minus x naught. Okay, so the fourth here is equal to f prime of 1. Okay, and a equals 1. That's our a. Okay, so that's what they mean when you're going to let a equals 1. Okay, and that would make sense because when x equals 1, that's where the tangent line touches the function. That's the x value. And then, of course, y here, the y is equivalent to f of x, right? So we find the tangent line. So like when you found the tangent lines, for instance, on problems in your homework problems on the exam, you get y equals the line. In this case, y equals a fourth x plus 7/4. But for section 3.9, it's convenient to recognize that this y, this line, we can call it the function L of x. It's the linearization of our function. And notice that if you want a general formula for L of x, the linearization of our function f at a, x equals a, L of x is going to be equal to f of a plus f prime of a times x minus a. That's the linearization formula. But what you're doing is you're finding the tangent line. That's what you're doing. Are there any questions so far? Sure. All right. So what we're doing, Kelvin, is we're finding the note here. This note. It's so in the book they give a formula for the linearization of a function f at a, and that formula is L of x equals f of a plus f prime of a times x minus a. But that it's the same thing as finding the tangent line of the function at a point. It's the same process. Okay, it's the same process. All right. So now what we want to do, are there any other good questions? All right, well now what we want to do is we want to utilize our tangent line, our linearization, to get these approximations to the square root of 3.98 and the square root of 4.05. So let me show you how this works. Okay, let me show you how this works here. All right, I'm going to note, I note here at the top that when x is near 1, the square root of x plus 3 is approximately, this is approximately, right? This symbol is approximately. When x is near 1, our function, the square root of x plus 3, is approximately equal to 1/4 x plus 7/4. We saw that from the picture, right? The tangent line very closely resembles the function when x was near 1. And in our case, we felt that when x was between 1/2 and 1.5, the tangent line was a pretty good approximation to the function. Okay. Now, what's pretty good mean? Well, okay, we won't worry about that right now. Because what we're doing is we're going to be sticking to values like square root of 3.98, square root of 4.05. Those are very close to the square root of 4. Okay, very close to the square root of 4. Notice when x equals, I'll just mention this in passing, that if you do the linearization when x equals 1, the linearization when x equals 1, well, that's going to equal 1/4 times 1 plus 7/4. I'm making just a little note here. So if we let x equals 1, the linearization when x equals 1 would be 1/4 times 1, because that's your x value, plus 7/4. That's just going to equal 8/4, which is 2. And notice that is going to equal perfectly the square root of 4. Okay, so at a, at the value of a, the linearization function equals the function you're trying to approximate perfectly. But what we're doing is we're sticking close to values that are close to the square root of 4. So square root of 3.98, what would the approximation be there? Well, what I do is I'm using my linearization formula. The linearization, it would be of 0.98 because 3.98 equals 0.98 plus 3. That means x is going to be equal to 3.98, equal to 0.98. Okay, so the square root of 3.98 equals the square root of 0.98 plus 3. So then the 0.98 is the value of x, right? Because our function is the square root of x plus 3. So if we're looking to find the square root of 3.98, then x is 0.98. Well, what's the linearization of 0.98? We apply the formula, the linearization formula that we derived. And what I've done here is I've done just some basic calculations to show you that we don't need a calculator at all to get this approximation. I can take 0.98 and divide it by 4. I mean, we learned how to do that in elementary school, didn't we? How to take decimals and divide them by numbers. That's no problem. And then I can add 2 decimals. 7/4 is 1.75. So 0.245 plus 1.75 is equal to 1.995. Okay, how many do this kind of thing, adding decimals, when you balance your checkbook? How many do have that experience? It's good practice. How many do that? Okay, Nicholas knows what I'm talking about. We don't. So the point is, we found an approximation to the square root of the square root of 3.98. Using our linearization. Linearization is telling us that the square root of 3.98 is 0.995, 1.995. Now in our calculator, try putting in the square root of 3.98 and see what the calculator gives you. Rounded to 3 decimal places, well, Do you get on your calculator 1.994993734? Or the square root of 3.98? Yeah, that's 1 point, and Ian gets that. So the calculator gives you 1.994993734. Well, rounded to 3 decimal places, that equals 1.995. See? So see if you're ever, remember that movie Castaway? Remember that movie Castaway with Tom Hanks where he's on the desert island? And he has to get himself on his island, off the island? Nicholas knows that movie. How many remember that movie? Sure, Joe knows what I'm talking about. Well, John, okay, rent it. You can probably rent that, or that might be available, in your cable TV. But the point is, he had to do. I mean, look, I hope you're not on a desert island someday like Tom Hanks was. But if you are, you're not going to have a calculator. But that doesn't mean you can't compute square roots of things. All right. So is that motivating? Is that kind of motivation there? A little motivation? I don't know. Good analogy. Good. Okay. A little bit. Yeah. Well, but John, calculator is important. But remember, in the calculator, how many are in computer science in here? Who's computer science major? Okay. Well, what programming did they do in the calculator, John, to produce these approximations? Maybe a linear approximation program. And the square root of this 1.995 is going to be an overestimate. Why is that? Well, if you go back and look at your tangent line here, okay, if you look at your tangent line, which is the linearization of your function, is the tangent line above or below the function? Is it above or below the square root of x plus 3? It's above it. That's right, Zoe. So when you're at 0.98 here, here's 0.98. Which is a little bit to the left of x equals 1. When you're at that, and if you just and this is obviously not perfect scale, but you pass a line up there, the approximation based on the tangent line will be a little above the exact value of the function. It's very, very, very good. Very, very, very good. Okay, so so any approximation using this linearization is going to be an overestimate. Now we can do the same thing for 4.05. 4.05, if you want the square root of 4.05, the square root of 4.05, again, remember what our function was. Our function was the square root of x plus 3. So 4.05 equals 1. Okay, hold on. Okay, our function is the square root of x plus 3. So 4.05 then would be equal to 1 square root of 1.05 plus 3. That's how you determine your x value. And this time I just put it in, and you can see you get an overestimate. Well, the estimate is 2.0125. I didn't go through, but you could get that answer through simple math. You could get it. And I'm curious, how good is that approximation? Well, let me put it in on the calculator, which calculator has a little bit more advanced programming in it, but the calculator for the square root of 4.05, I get 2.01246. Okay, so there's not agreement in the fourth decimal place, but it's not bad, not bad. And notice that the approximation is higher. The approximation based on our linearization is higher than what the calculator gives you, and we're assuming the calculator answer is pretty close to the real answer, exact answer. It's an overestimate. So Kelvin, how is it an overestimate? Overestimate means your approximation's higher than the true value. An underestimate means that your approximation is lower than the true value. That's what we mean by over and underestimates. Okay, good question, good question. Okay. All right, are there any questions on this? Any questions at all? Oh, how did I get 1.05 again? It's because let's see, the square root of 4.05 is equal to the square root of 1.05 plus 3. So like, for instance, say that you wanted to estimate, let's say that you wanted to estimate, hold on here, one moment here. Let's say you wanted to estimate the square root of 4.12. Well, what's your x going to be? 1.12. That's right. Good. That's right, because 1.12 plus 3 equals 4.12. That's right, Lynn. Sue, are you comfortable with that? Okay, good, good, good. All right, are there any other good questions? All right, I'll stop the recording.